Hello, yesterday we solved this problem. I put the ramp the other way and we got that if we put the frame of reference this way, it's very convenient because the friction and the normal force are on the x on the axis, so you don't have components for the friction and the normal force. You only have components for the gravity. And when we solve this problem, we got the first equation and here the acceleration is the acceleration in the x-axis, the acceleration in the y-axis is 0, so it's very convenient to put the axis in this direction. But I always get the question, why not to do it with the axis like this? And that's what we are going to solve today. And this is the one that is 0 because of the choice of the axis. And I think this is what I found that people don't understand. That the reason is not only that the normal force and the friction won't have components, only the components are for the gravity. But that's not only the reason. The reason is that the block does not move in the y-axis. The block does not move in the y-axis, so the acceleration in the y-axis is 0. And this is the empirical equation that relates friction and that. So we solve this problem. We get that the acceleration is this expression that we got yesterday. But this is the magnitude of the acceleration, and that is and this is 0, so it's the acceleration in the x-axis. So because this is the magnitude of the acceleration, we are supposed to get the same expression over here. The same expression over here. But here, the y component is not 0. So first, you have to understand that, yes, the acceleration is constrained to the horizontal plane, meaning that you have the y component and the x component. And the other thing is that if we put the axis like this, then here is the normal force, mg, and friction. Is very inconvenient because now, yes, mg doesn't have components, but now both the normal force and Fk have components. So the problem ends up being mathematically more complex, but the solution is supposed to be the same. So I draw over here the axis again, and now you have to be careful because if this is the angle of the ramp, then this is the angle of the ramp, then this is the angle of the ramp, but this one here is also the angle of the ramp, because these two are 90 degrees, and this size is at 90 degrees, and this size is also at 90 degrees over here. So this is also the angle. And yes, the only good thing is that MG doesn't have components, but now the normal force has component, the friction has component, and there is acceleration in the y-axis, just because I put the axis like this. So the equations are going to be Fk cosine of the angle, this piece over here, and plus n sine of the angle, this piece over here. And then the other equation is going to be n cosine of the angle, this piece over here, positive, and Fk sine of the angle, mg without components, that's convenience. And now there is acceleration in the y-axis. And now this looks that cannot be solved. And yes, we know that friction is mu k times the normal force. So I'm going to rewrite the equations like this. And this is the like cannot be solved because this is a system of two equations, but I got my unknowns to be n, ax, and ay. So I need a third equation. That the third equation is the constraint that the block moves along the horizontal. So that means that tangent of the angle is ay over ax. And by the way, the acceleration here is downward, so it's supposed to be a negative over here in that equation. So I got, this is my third equation. But I found that it's better to go back and put the magnitude of the acceleration is ax, ax is a cosine of the angle, and ay is a sine of the angle. Again, because this is my angle, this is a, this is ay, and this is ax. And now, instead of using the tangent, this constraint equation, I will use put everything in terms of a, and this magnitude of the acceleration, which is also that can be written like this, but it's not convenient. It's not convenient to write it like this. This value of a is supposed to be this, because the magnitude of the acceleration is an invariant, does not depend on your choices of the axis. So I wrote equations over here again. Now we got a system of two equations, two unknowns, and also the normal force. The magnitude of the normal force is independent of the choices of your axis. So in yesterday we got that the normal force is mu mg cosine of the angle, which is this equation that we got over here when you choose the axis in this way. So that's supposed to be the same answer as well. And so we are supposed to get that for n as well, and the same equation that we got yesterday for the acceleration. So how to solve this system? I think that the easiest way is to multiply this times sine and this one times cosine. You're going to see in a moment why. So there is a minus over here that I forgot to put. And now I multiply the first one times sine and the second times cosine, because this term on the right hand side of the equations of the system of equation is going to cancel out. This cancel out. Also these terms over here and this one cancel out when I add it up. And you know that sine plus cosine squared is 1. That's the fundamental identity of trigonometry. So I get n common factor sine squared plus cosine squared minus mg cosine of the angle equals 0, and this is 1. And I get exactly what I got with the other choice of reference, because that's the magnitude of the normal force. It's an invariant. It's independent of the choice. It's independent of the choices for the axis. Okay, so now once I got the normal force, I can substitute it on the top or bottom equation. I'm going to substitute it here on the top equation. So I got mu k mg. Let me pause the video and write it down. I substitute the normal force on the top equation over here and over here, so I get cosine squared, and then I get sine cosine, and now I divide everything by the mass and cosine of the angle. Cancel, the mass cancel, and I get exactly what I got yesterday. I got exactly what I got yesterday, because again the magnitude of the acceleration is invariant or independent of your choice of the axis. Now, why to use this choice of axis? Because maybe if you're doing a simulation, you want to do a simulation of a block sliding down the ramp. Probably if you are programming and doing the simulation, this choice is more convenient. Although it's mathematically more complex to solve the problem, it gives you exactly the same values for the magnitude of the normal force and the magnitude of the acceleration. Now, if you want to go back to ax and ay, it's just a cosine of the angle and a sine of the angle. And this is probably what you will use if doing a simulation with the axis like this.